This is section 6.3. We're going to cover two big theorems, the ODT, orthogonal decomposition theorem, and the BAT, best approximation theorem. The ODT is an extension of what we did last time. So let's review what we did last time before we talk about the orthogonal decomposition theorem. So suppose y and u are two vectors in Rn, and w is the line spanned by the vector u. If y hat is the projection onto u of y, then we can decompose y into y hat plus z. What's y hat? Y hat is projection onto w of y, which in formula-wise is y dot u over u dot u, u. And that vector lives in w, meaning it's parallel to u. It lies on the line spanned by u. And so if this is the vector u here, w is the space spanned by u, so that w is that whole line, and the projection of y onto w is y hat. And the other vector z, the formula for that is y minus y hat, and that lives in w perp. So this would be our z. And y hat and z are perpendicular, and their sum is equal to y. And the distance, the length of this piece here, that's what we call the distance from y to w, and that's simply the length of z. So the distance is going to be the length of z. All right, so let's do it with an actual set of vectors. Here's y, here's u. Right y is the sum of two vectors, one in w. So the one in w will be y hat. So y hat is y dot u, u dot u, u. So notice every time I use that formula, I write it down, and I'm going to want you to do that in your work too. So write that down, and you'll never forget it because you write it down so often, you'll be able to recite it in your sleep. Okay, so y dot u is -4 plus 14, which is 10. U dot u is 16 plus 4, which is 20. And I'm going to switch to linear notation. I'm going to write u as -4, 2 in parentheses. So that's 1/2 of -4, 2, which is -2, comma 1. So that's our y hat. And now z is the difference, y minus y hat, which is 1, comma 7 minus -2, comma 1, which gives us 3, 6. All right, and then we want to phrase our answer appropriately. So this question says, well, it's not a question, it's a statement. Write y as the sum of two vectors. So let's do that. Y is -2, 1 plus 3, 6. This is my y hat, and that's my z. And then the distance from y to w is the length of z, which is, let's see, 36 plus 9 is 45, square root of 45. Now, when you do this orthogonal decomposition of y, there's a safety check. So I'll do that over here. Check. There are two things you want to check when you find a decomposition like this. One, is y really equal to y hat plus z? So it seems obvious, but if it doesn't work, then it doesn't work. So let's add these two vectors. 3 plus -2 is 1, and 6 plus 1 is 7. So yes, when I add those two vectors, I get y. And the second condition is that y hat should be perpendicular to z. So check that y hat dot z is 0. So let's just check -6 plus 6 is indeed 0. So we did this problem correctly. Okay, so the orthogonal decomposition theorem is pretty much doing what we just did here, except now W doesn't have to just be a line spanned by a single vector. W can be a vector space spanned by a whole bunch of vectors. All right, and in this case, the only change is the formula for y hat. Y hat is still the projection onto W of y, but if you have an orthogonal basis for W, then you can use Theorem 5, the formula in Theorem 5, to write y hat like this. So the formula for y hat, rather than just being a single dot, a single, y dot u over u dot u times u, it's going to be a sum of mini projections, y dot u1 over u1 dot u1 u1 plus dot 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 up to y dot up. And here's a picture here. Y hat will live in W, which I have pictured here as a plane now instead of a line. And then Z will be perpendicular to Y hat. All right, so let's give it a try. Next page. Let W be the space spanned by U1 and U2. And we're given a Y. And first of all, we want to verify that U1 and U2 forms an orthogonal set. So the verification there would just be to take U1, dot it with U2, we should get 0. So 3 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, yes. So we can use the ODT. Find the orthogonal projection of Y onto W. All right, so I'm going to use that formula. In this case, I only have a U1 and a U2, so it's not that bad. Y dot U1, U1 dot U1, U1, plus Y dot U2, U2 dot U2, U2. All right, and that's, let's take Y dot U1, that is 10. U1 dot U1 is also 10. So I'm going to take 10 over 10 U1 plus Y dot U2 is 3. U2 dot U2 is 1. So I'm going to want U1, which now I'm switching to linear format, 3, 0, 1, plus 3 times U2, which is 0, 1, 0. So we add those two vectors together and we get 3, 3, 1. That's the orthogonal projection of Y onto W. Write Y as the sum of a vector in W and W perp. Okay, well, we've done most of the work. We want to write Y as Y hat plus Z. So let's find Z. Z is Y minus Y hat. Y is 0, 3, 10. And I want to subtract off Y hat, 3, 3, 1. And that gives us negative 3, comma, 0, comma, 9. All right, so Y is equal to 3, 3, 1, that's Y hat, plus Z, which is negative 3, 0, 9. Okay, and now let's do our safety check. 1 is Y really equal to Y hat plus Z? So let's just do that mentally. Negative 3 plus 3 is 0. That's right. 3 plus 0 is 3. That's right. And 9 plus 1 is 10. Okay, and the other part of the safety check is check that Y hat is orthogonal to Z. Is that 0? So we get negative 9 plus 0 plus 9 is indeed 0. Okay, so you can see that it's really exactly what we did for the very first review problem, except now W is spanned by 2 vectors instead of 1. Okay, here's a problem where W could be spanned by 3 vectors or 1 vector, depending on how you want to look at it. So we've got 4 vectors here, and those vectors form an orthogonal basis of R4. Write Y as the sum of a vector in the span of U1 and a vector in the span of U2 through U4. Okay, so there are 2 ways to do this. A smart way and a not such a smart way. The smart way would be to let Y hat live in W. So Y hat will be the projection of Y onto U1. And then over here, Z will be what's left. Z will be in W perp. But you could also find the orthogonal projection of Y onto W, where W is this space, spanned by U1, U2, U3, and then let Z be the leftover. Now, the second way requires more work, because if you let Y hat be the projection onto W, where W is spanned by U2, U3, U4, then in your formula for Y hat, you're going to have to do 3 different dotting expressions. In fact, here it is. You got to compute that whole thing. And then for Z, you just do subtraction. Okay, so we're going to do method 1, but we're going to see that method 2 gives you the same thing, except the labels on Y hat and Z are reversed. So first, let's find Y hat using method 1. Y hat's going to be Y dot U1, U1 dot U1, U1. Okay, Y dot U1. So here's Y, and here's U1. And if I dot, I get 4 plus 10, I get 14. And then U1 dot U1 is 4, 5, 6, 7. And that's going to be times U1, which is 2 U1, and U1 is 1, 2, 1, 1. So that's the vector 2, 4, 2, 2. All right, and then Z is just the difference, Y minus Y hat, which is, Y is 4, 5, negative 3, 3, and I want to subtract off 2, 4, 2, 2. And that gives me 2, 1, negative 5, 1. So Y is 2, 4, 2, 2 plus 2, 1, negative 5, 1. This is my Y hat, and this is my Z. Those are perpendicular. Y hat lives in this space W, Z lives in W perp. That required a minimal amount of effort. And doing it the other way, you can see that I'm getting the same vectors, 2, 1, negative 5, 1, and 2, 4, 2, 2, except now I'm calling the 2, 4, 2, 2 Z, and the 2, 1, negative 5, 1 is Y hat. So you're getting the same decomposition, it's just the labels are reversed. So if you do have a choice, and most of the time you don't, most of the time problems are phrased like this, where you have no choice. But if you do have a choice, I suggest you pick the one that requires the least amount of work. Okay, so we'll pick up with a second video for the BAT, the best approximation theorem.